this list. I know I need to upload this list for you guys for what's going to be on chapter 3, but I'm still kind of building it. But, I'll put it up soon. So all this stuff in chapter 9, I haven't gotten to this one. It says not covered yet. Not section 9.10. But I'm going to go ahead and do calorimetry. And do something similar to this for our next lab. And then I'll do some of the gas ball stuff today. Chapter 10. But for now, you still going? This is example 9.8. This example 9.8. So calorimetry, this is how we find these heats of reaction that we've been messing with. Finding delta H of reaction. So if you look at this, it tells you the setup. Magnesium, HCl. That's solid. This is aqueous. So if you want to know the delta H for this reaction, basically put it in a little chamber that is insulated, and we'll do this in styrofoam cups. They work very well. It's called a calorimeter. And the information you've got here is, you read through that paragraph. Those of you who do not get a picture. Magnesium is put in. Other information you need. There's 100 milliliters. So you have 100 milliliters of the HCl solution and 0.158 grams of the magnesium. What you do is, as soon as you put the magnesium in there, you seal it up with a thermometer in there, and the temperature changes. Initial temperature, the final temperature, 32.8. A couple other bits of information. That's the density of the solution. Density of the solution. And they tell you the heat capacity of the solution. We'll call C. Is 4.18 joules per gram degree C. From that information, you can find the delta H of reaction. All right. We've solved problems like this before, where you have some number of joules, and you multiply by mass. I would always do it over 1 when I was doing it before. Delta T times the heat capacity. multiply those three things together, it tells you the heat. That is some number of grams, the delta T, and then the joules per gram per degree C. Grams cancel. This is degree C, so that cancels, and that tells you the joules. So we saw something like that before. Sorry. But we can get a delta T here. We've got our, the grams here are going to be the grams of the solution, the total grams of the solution. Think of it. Did they do it that way? Yeah, they did. Grams of the solution. And that's why it gave us density. If we've got 100.0 milliliters, and it's 1 gram per milliliter, that means we have 100 grams. That makes sense. I mean, more formally, it's 100.0 milliliters, and it's 100 grams to 1 milliliter. No. No, write it down. The density is 1 gram per milliliter. Or 1 gram per milliliter. Sorry, this was density is 1 gram to 1 milliliter. So we basically have 100 grams. Our delta T here is final minus initial, 32.8 minus 25.6, 7.2 C. The delta T is 2 degrees C. And they told us to use this for the heat capacity of the solution, 4.18 joules per gram, 1 gram, 1 degree C. Fat ones here. All right, so what do we get here? That tells us 7.2 times 4.18. 6 joules. That's how much heat was generated. Yeah.
How can we use 100 grams when there's 1.158 of the magnesium?
It's telling you the solution after the reaction, the density of the solution after the reaction, so it's involving. It's involving the magnesium. That is the density of the solution. 1 gram per milliliter of that magnesium solution. This is a gas that just goes away. The density of that is 1 gram per milliliter.
Absolutely, because we have 100 milliliters of magnesium.
Yes. Oh, I think they got something to say. Yeah, they got the same thing as that. Okay, good. This is how much heat was generated out of the solution. So really it's negative. This is three significant figures, 2 and 3. So I guess what we have to do is 3 point. That's how much came out of the solution. So that tells you the delta H. I could write it like this. So now I could say delta H of this reaction equals that's really not quite right, because we need this per mole. So let me do the per mole part. So how many moles of magnesium went in here? We put grams. And magnesium is 24.31 grams per mole. Did I say 24.31? So how many moles do we have? 158 divided by 24.31 equals 0.00649938297. 4 significant figures, 3 significant figures. So it's 650. That's how many moles of magnesium we put in there. So we really need this in joules per mole. So we have to go so the reaction as is, the way we did it, we put this many grams of magnesium in. That turns out to be this many moles. And that's the joules that came out. So really, we have to go.
So you're always going to use that negative number?
Huh?
You're always going to use that negative number? You're always going to use the negative sign?
If heat came out, yeah. Here's how you know. It went from 25 up to 32. That means heat came out of the magnesium.
Okay, that's usually.
3,000 joules divided by 0.00650. That's what my calculator tells me. We have 3 significant figures. The 5 rounds to 1, so 462,000 joules per mole. So really, okay, 4 kilojoules. 4.6 times 10 to the 5. I kept one too many significant figures, I guess. Should be negative. Really 2 significant figures? Yeah, because that one was 2. So it's 6.0. Really should have kept that. way to follow that? You want me to do another one? I'll do the other one in that example. But this delta H that we've been working with all this time, that's what I just calculated. Books always do this. They use the letter Q, the heat, and then they go M, delta T. C for heat capacity, I'm used to seeing it as CP. For some reason they're saying it's CS solution, but let's just keep it as C. This other example, I'm going to do this other one 9.8. So we're given AgNO3, silver nitrate, aqueous plus HCl, aqueous. Put those two things together and you get GCl, solid plus. The question is, what is the delta H of reaction? So 50 milliliters of 1 molar HNO3, 50 milliliters of 1 molar HCl are poured together. The temperature changes. Temperature initial is temperature final is 24.2. Calculate the delta H for the reaction. We're using density of 1 gram per milliliter. And again, they're telling us to use C as a for 1 gram, 1 degree C. So we calculate our delta T. We use this for C. And I guess we get the mass from, well, if it's 1 gram per milliliter, like it was before, 50 milliliters plus 50 milliliters is 100 milliliters. So we have a mass of 100 grams, because it's 1 gram per milliliter, and we have 100 milliliters. The delta T, actually fraction. Grams, degrees C, and this is joules per gram per degree C. And what we get for joules then is 0.81 times 100 times 4.18. I guess we're keeping two significance figures, so it's 340 joules. All right. We same. 1 molar AgNO3. We have 50 milliliters, and it's moles per liter. Moles per liter. We got 1 liter. So, the moles we need. That'll tell us how many moles of HENO3 we have. It's also the same number of moles for HCl. So 50 times 50 divided by 1,000. That's how many moles we have. So to get this in joules per mole.
Excuse me, Dr. Emory.
Yes.
I must have missed this part. What did you do up at the top left corner? And what is that? M, I'm guessing, represents moles.
Here.
Top left corner. What's
That's mass.
And then what's Q?
It's mass. Q is just, all textbooks use that as a variable representing the joules.
That's just joules.
Just means heat. That's the letter they use. It's kind of like, just like half awake. If I said, I could use that symbol for density, but the units would still be grams per milliliter or something. They use that for the represent the heat that comes out of the reaction. And it could be in joules, it could be in calories, but that's just the unit they use. This is such an easy thing to remember that I'm using it, but really what I'm talking about here is joules. Q is just a general term for heat. So I've got 340 joules that came out, divided by 2.5 moles. So the way I want to report this then is 340 divided by 2.50.
Doctor, in your equation, does it say that I don't know HCl is whatever it's 0.1
Does it?
mole per? Yeah.
Yes, they do. These were 0.1 mole. Did it say 0.100? Which makes this. Why did I use 50 there? I knew all that later. 0.100. 50 times 0.1 divided by 1,000. So if it's that, 0.00500 moles, 340 divided by 0.005. I have two significant figures there, so I'll have to go. So I can write. So this there's only one mole of this, so I can write that this way instead of joules per mole.
Where did you get the 338, 340?
Where did I get the 340? That was mass, which was 100 grams, times the delta T, times the heat capacity. I got this, but since I only had two significant figures here, I only kept two significant figures. The 8 rounded to 3. You guys okay?
Where was the 100 grams from? On the max? I'm sorry.
50 milliliters and 50 milliliters, so we had 100 milliliters.
Okay.
And then the density tells us that it's going to be 100 grams. I'll save. Jump to pressure. So we're going to go to the gas law stuff in chapter 10. And now we have to start working with pressure. And for some reason, there's a million different units for pressure. I don't know why all of these still persist in science. But I have, this is a table 10.1. And I'll give you these on the test, but there's something called the Pascal. There's pounds per square inch. I'll tell you what these numbers are here. There's the torr. Also, 1 torr is also 1 millimeter of mercury. Let me get these written down. 29, 92. There's also the bar. Atmosphere. These numbers are showing what the different measurements are at sea level on Earth. But it also works as a way to convert between one pressure and another. So those are basically how you get conversion factors. So let me go to, this is 10. And things to solve is just conversions. So, let me grab, so you'll have those on the test. This isn't hard. I'll do these at 26, but 25 and 27 are just like 26. The pressure on top of Mount Everest averages 235 millimeters of mercury. 235. You've heard of mercury. It's a metal, but it's a liquid metal at room temperature. You've heard of mercury, right? If you put mercury in a U-shaped tube and you seal one side of it, and both of them are level, however much pressure pushes down on this one pushes it up some, and that's where we get the millimeters of mercury. So that's one way to measure pressure. Just in case you're wondering what the heck millimeters of mercury is. This one, this one of these. inches of mercury. Torr is 760. Torr is millimeters of mercury. There's also inches of mercury. What else? Bar, atmosphere. 760. This is 29. 2. So lots of different ways to represent.
And we'll get that chart on the test, right?
Yes. So this question is asking me. So this is essentially saying if I have 235 millimeters of mercury, what is that in torr? It wants me to do PSI, inches of mercury. Okay, to do these conversions, it gives me 235 millimeters of mercury and says, what is that in torr? To get the conversion, you get 760 for torr, and the millimeters of mercury over there. Oh, is it millimeter? I better look. This is going to be 235. Millimeters of mercury, no, it asks for inches. It did ask for torr. All right, we'll just be in trick. Torr is millimeters of mercury. So this one just comes out to if I wanted in inches of mercury, I get the inches of mercury from over there, 29.92. Millimeters is 760. So that is 235 times 29.92 divided by 760. So this is I wanted in PSI. PSI is 15.7. This is 760. 235 times 14.7 divided by 760. That's pounds per square inch. Atmosphere is 1. 760. Yes.
Where did you get the 760 million?
I get the what?
The 760.
Millimeters of mercury from here. Torr equals millimeters of mercury. They're the same unit, really. 1 torr is 1 millimeter of mercury. Torr is from a guy named Torricelli. These all just, I don't know why we have so many of these. There's a guy named Pascal that came up with that one. Inches of mercury, millimeters of mercury. I forgot where bar comes from. Barometric being the word for pressure. Anyway, that's how you do these conversions. So as long as you have this in hand, these aren't hard. And I will give you those in the test. Okay. So pressure, and then the next thing is 10.5. Ideal gas law. I'm not sure which of these. I think I'd rather have you use this PowerPoint that I made. So there'd be a PowerPoint called Gas Laws. It's the best thing to look at to practice these types of problems. Do something. Insert text box. Bring to front. Format, shape. Solid fill. PV equals nRT. Any of you who took chemistry before, do you remember that? PV equals nRT. Ever seen that? No? Okay. It works for very small gas molecules. And gas molecules that don't really interact with each other. B is volume. N equals number of moles. T equals temperature. And the R is a constant. R equals 0.080. Have to use a temperature of Kelvin for these. So basically, you want your pressure in atmospheres to use this constant. You want your pressure in atmospheres, your volume in liters, your amount of substance in moles. Kelvin, that's the units here. So let me show you how this works. I explain this different than most textbooks, which is why I skipped 4 that I skipped. 10.4. You get these simple gas laws in route, the way I do this. Okay. So the header here is when you're changing from one state to another. There's another situation when you're not changing from one state to another. That one is the one that really involves the R value. So read this question. The first one, slide 2, on my gas laws PowerPoint. The pressure of a gas is 2.30 atmospheres in 1.80 liter container. Calculate the final pressure of the gas if the volume is decreased to 1.2 liters. Okay. Here's what you do. You've got pressure, volume, number of moles, and temperature. So you have one state where you have all these defined, and then another state where you have all these defined. What you do is first decide what's changing and what's not. If something's not mentioned in the problem, then it's not changing. All right, so this says pressure of 2.3 atmospheres. What's the calculate the final pressure? So pressure is changing. 2.30. And we're being asked for that. All right, what else is mentioned in the problem? 1.80 liters, and then the final volume is 1.20 liters. This was atmospheres. Temperature in moles has not been mentioned. You see that? Sometimes it'll say, in parentheses, temperature stayed constant. But if it's not mentioned, then it stayed constant. So, if you can get that far, identify what you've got, then you go, you take that formula, you take what's changing and you want it on the left side, and what's not changing, you want it on the right side. This one's already set up, though. If you just write down PV equals nRT, it's pressure and volume that are changing. N isn't changing, T isn't changing, R will never change because it's a constant. Let me do this one. Let me do this one just because there was no algebra needed here. Sorry, let me skip up to this one. Let's go to the next one, slide 3. What will be the final volume? Question mark. 3.5 liter sample of nitrogen. So we are at 3.50 liters. What is going to be the final one? Okay. 20 degrees C is heated to 200 degrees C. Over there on the right where it says convert temps, we have to have our temperature in Kelvin here. So there I am converting 20 degrees C to K and 200 degrees C to K. So it's 293.2 is initial. Okay, initial. And the final is 473.2. And again, notice nothing else is mentioned. So that's constant and that's constant. So now, your next step, once you identify what's changing and what's not, you want to get the things that are changing on the left and the things that are not changing on the right, using algebra. We want pressure on the right because it's not changing, so I divide both sides by P, and I get that. Divide this side by P, divide this side by P, you get that. We need volume over here, and we also need temperature over here. So I'm going to divide both sides by T. Divide both sides by T. You with me? So I decided that moles and pressure are not changing, volume and temperature are changing. I started with this formula, and I worked it so that I had the things that are changing on the left and the things that are not changing on the right. You with me? Then you just do this. You take what's on the left, you go V1, T1 equals V2, T2. And now you've got 3 out of 4 of those variables you just solved for the last one. We're trying to solve for V2. So I'll multiply both sides of these by T2, so I'll have V1 times T2 divided by T1 equals V2. All I did is multiply both sides by T2 to get V2 by itself. Just one more quick step of algebra. You with me? And now I can just plug in those 3 values and solve for V2. We've got V1 is 3.50. T2 is 473.2K. And then T1 is on the bottom. 293.2K. And that's it. That'll tell you what the new volume is. I skipped that first one because P and V were changing and these were not, and then I wasn't going to get to do any algebra. But if it's P and V changing, then you just use it as is. If it's P and V changing, then this is where you think P1, V1 equals P2, V2. I guess I could finish solving it, but the solutions are on here. Here's the solution to that. Oh, I deleted a slide. Let me do something here now. So there's a solution to that one. Okay, here's one where 3 things are changing. The gas sample occupies 22 liters at 171 C and 1.43 atmospheres. Calculate the volume of the gas if the temperature and pressure are increased. Okay. And notice we haven't used this yet. That'll come up on the next few slides. So tell me what's what here. What's pressure 1? Yes, 1.43 atmosphere. What is pressure 2? What is pressure 2? There you go. What about volumes? What is volume 1? .0 liters. What is volume 2? Volume 2 is question mark. That's what we're looking for. Is number of moles mentioned there? So that stays constant. And what are the temperatures? I've got them converted up there already. Just add 273.15. It's degrees Steve. So the initial one was 444K. And T2 470K. All right, so we start with pressure and volume are changing. Moles are not. Temperature is changing, so we need temperature on this side. So we just divide both sides by temperature. So that's everything that's changing, and then you just go P1, V1, T1 equals P2, V2, T2. And you have all these variables but one, so you solve for the, I guess we're solving for V2. Divide both sides by P2, multiply both sides by T1, T2, so we'll have P1, V1, T2 over T1, P2. There's your plug and chug formula. I've got milliliters written in there. You guys follow these? So do look at these and make sure you're able to do it. Ideally, you just look up here at the word problem and you don't peek at all the solution. I could make quizzes out of these, but I just want you to have them in hand and see if you practice. The other way you use PV equals nRT is it's when nothing's changing. There's not P1 and P2.
Could you just explain, kind of go through that equation to the formula that we see again?
This. Start with PV equals nRT.
I think I get everything except how you get.
Okay, it's just algebra. You just missed a step of algebra. Those are the things that are changing. So I want all of those on the left side, and I'll leave the NR on the right side. Algebraically, what that means is I divide both sides by T. You okay so far? All right. And then I'm going to take that and rewrite it as P1, V1, over T1 equals P2, V2, T2. Since we're solving for V2, I want V2 by itself on the right side. You with me? If I multiply both sides by T2, that gets rid of this. Multiply both sides by T2 over 1. You see that? Multiply both sides by T2, that goes away, and we have T2 times P1 times V1 over T1. See what I mean? Does that make sense? And over here, what I have left is P2 and V2. You with me? After I multiply both sides by T2, this is what I've got. You with me?
So you would divide P2.
Yep, now I divide by P2. P2 cancels. And now I can plug and chug. I've got all 5 of these variables. I just solve for P2. That makes sense? So in that case, 3 things will change. And you can have all four of them change too, you do the same thing. The other way to deal with these, and you read this from the context, you read the problem, and you decide, are things changing or not? And if things aren't changing, then you're going to use the R value. Notice, so if you read that one, sample of hydrogen gas is added in this is slide 10, a sample of hydrogen gas is added in a 5.80 liter container at 56 degrees C. How many moles of the gas are present in the container if the pressure is 7.6 atmosphere? The point is, there's nothing changing. There's not an initial or final anywhere. So, it's asking for this. It's asking for the number of moles. In some sense, this is the easier type. So 670 atmospheres, 5.80 liters. And the temperature after converting is 329.2 Kelvin. Truthfully, that should only be 3 significant figures. Really, that should only be 3 significant figures. No, that's right. Yeah, 1 after the decimal. That's right. Okay. So all you're going to do is use this and plug and chug. You're going to use this for the R value. And we're solving for n, so I would go ahead and manipulate it with some algebra. You see what I did algebraically to get to that? I just divided both sides by nt. And then you just plug and chug and you can find n. So look at the blue ones. Practice solving one of those. Okay, involving grams. Here you're just going to convert from grams to moles, and then everything else is the same. So look at the first yellow one. A 2.65 gram sample of CO2 gas is placed in this many liters. Calculate the pressure inside the vessel if the temperature is 35 degrees C. So you see the conversion up here to 308.2 Kelvin. And then you just find the grams per mole for CO2 and convert that to moles, and then you have everything. You see that? So I guess I just didn't like the way they did questions back to that chapter. So I just want to use this PowerPoint for problems to solve. We'll get that uploaded to Microgas Law. But let me show you one more thing about these. Because books like to do this first, and then, but really, everything I just described to you will get you there. In between 10.3 and 10.5 is 10.4, and they do Boyle's Law, Charles, Boyle's Law, I just remember it like this. Actually, I forget these a lot. This is one of those things that in science just makes me mad, and I don't know why they do it like this. All right. PV equals nRT. If it's temperature and pressure that's changing, what I've told you to do is manipulate this so you have R over V, and then you would go P1, T1 equals P2, T2. That's an expression of Boyle's law. Any combination of these, you could come up with a name for. It's just Boyle was the first one to figure this out. So if you increase pressure, you increase temperature. What do I say this? Yeah, let me leave it like this. That is one way to state Boyle's law. But I think it's easier to look here and go, okay, if that's constant, that means if I have, do it like this. If that has to stay constant, and I have, let's say I have a pressure of 100, temperature at 10, just to make things up. That means this equals 10. The constant is 10. So if I get a new pressure, it's 200. For this to equal 10, what does my new temperature need to be? So this is P1 equals 100, T1 equals 10. That would mean if you calculated that, this would be 10. If your new pressure is 200, what is your new temperature? If it's got to equal 10, then this is 20. So when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. These are what we would say directly proportional. Volume and temperature, Charles' law. If it's volume and temperature, I would have volume over T and R over P. This is my constant. And these are the same way. If volume goes up, temperature goes up. If volume goes down, temperature goes down. Directly proportional. Okay, this is one. Pressure and volume. This is one. Boyle's law is volume and pressure. Oh, that's what it is. Boyle's law is volume and pressure. Volume and pressure. Volume and pressure. I don't have to manipulate this. So these are inversely proportional, not directly proportional. Meaning, if pressure is 10 and volume is 100, that means the constant is 1,000. If I take pressure from 10 to 20, how am I going to get that to become 1,000? Why can't I do that in my head? That's crazy. This would have to be 50. So in this case, pressure goes up, the volume goes down, so those are inversely proportional. You guys okay with that? I guess I have to decide what else I'm doing in this chapter. Partial pressures. All right. We are so far ahead. Struggling what to do. We'll do a lab, maybe 2 next week, so that's where all our time's going to go. Maybe we'll do 1 lab after break. All right, I'll decide what else to cover in chapter 9 and chapter 10. Let's just stop there for now.
Thank you.
So we are way ahead. Brian thought we were behind. We'll have a few extra more.